Here we've been given the number of molecules of a particular polymer as well as its molar mass. We have three different polymers. One of 25,000 grams per mole, one of 50,000 grams per mole, and another one of 100,000 grams per mole. So we are being asked to work out the number average, the weight average, and the Z average. First, what we should really consider, we can consider a graph of essentially our total mixture of polymers. What we have at the bottom is the molecular weight. We'll just give that as M, and here we have the fraction of polymers with a particular weight. So normally this will take a Gaussian distribution, a Gaussian curve for its distribution, which looks roughly like this. At the top of here we'll have Mn, and around there we'll have Mw, and at the bottom we'll have Mz. And what this tells us is our Mn value is always going to be smaller than our Mw, which is in turn going to be smaller than the Mz value. So if we are obtaining answers towards the end which dispute this, so we have Mz which is smaller than Mn, it means that somewhere in our calculations we've gone wrong and we have to amend that. So on to the actual question. We'll be using the standard formula you've been given for calculating the number average, and that is simply Mn equals the sum of Ni Mi over Ni, where Ni is the number of molecules and Mi is the molar mass. So the I value here is just an algebraic term which is essentially specifying which polymer we're looking at. So if we go back to the question, we see that we have 300 molecules of a polymer of molar mass 25,000 grams per mole. So if we think about that, it will be N1 and M1, and that will equal 300 for M1, the number of molecules, and 25,000, the molar mass of that particular polymer. And again for N2 and M2, this is 500 molecules and a molar mass of 50,000. And then again for M3 and M3. These are 250 and 100,000 respectively. So if we put this into equation form, essentially we're going to be looking at N1 times M1 plus N2 times M2 plus N3 times M3, and this will be all over the sum of all the N values, so N1 plus N2 plus N3. So if we insert our values now, we get 300 times 25,000 plus 500 times 50,000 plus 250 times 100,000, and this will be all over 300 plus 500 plus 250. So you can do this on your calculator quite simply. I already have the answers written down obviously, so if I plug those in, you should end up with 57,500,000 over 1050, which gives the Mn to equal 54,762 grams per mole. minus 1. Don't forget about getting the correct units, because examiners can be very strict on that. You can get marked down very easily for getting the wrong units there. So the next part of this question is the determination of MW. This takes a slightly different equation, where we are looking at the sum of Ni Mi squared over the sum of Ni Mi. And in these type of questions, they're very common in this course, it's quite important in terms of saving time to recognize that this here, this sum of Ni Mi, is exactly the same as the numerator we calculated in the first question. So if we split this up into what we should be looking at, as in we put in all the numbers, we get 300 times 25,000 squared. It's important here we see that Mi is squared, not the whole thing, just Mi, plus 500 times 50,000 squared, plus 250 times 100,000 squared. And that will be over the numerator we calculated in the last part, which was 57 million. I'm just saving time on that. If you were to put it in fully, you would do the sum of Ni times Mi, so it would just be over 300 times 25,000 plus 500 times 50,000, etc. So if we calculate that top part on our calculators, we are left with MW being equal to 3.94 times 10 to the 12 over 57,500,000. So this is equal to 68,478 grams per mole minus 1. Now, the last part of this is MZ, the Z average, and this takes the form of the equation Ni Mi cubed, remembering to only cube the Mi, you're not cubing this part here, and that's over Ni Mi squared, in other words the numerator from the MW question. So bearing this in mind, we can plug in the values. We have 300 times 25,000 cubed plus 500 times 50,000 cubed, in brackets again, plus 250 times 100,000 cubed, and that again, you should probably draw your line slightly better than this, is over the numerator from the last question, so that is 3.94 times 10 to the 12. And if we work out the top part via the calculator, we are left with MZ is equal to 3.17 times 10 to the 17 over 3.94 times 10 to the 12, and that is equal to 80,504 grams per mole minus 1. And then if we remember what we said at the very start, where we are taking into account this Gaussian distribution, we want Mn to be less than Mw and Mz, so Mn is 54,000, our Mw is 68,000, and our Mz is 80,000, so that completely fits with that.